So, welcome back. After understanding all about the tables and also about the Mollier chart which I explained to you just now, let us now go into applications of the properties of fluid and basically apply these for using the first law, where the direct application of all these things what we have learned till now can be shown. The first example I will take using a Mollier chart, which will not use after that, and the first example therefore will show you how to use the Mollier chart, how can a process be seen on the Mollier chart. But this will not normally be used for solving various problems, and therefore after the first example I will use steam tables all through for getting the properties of water at various pressures and temperatures, and that is why the first problem is little special. Other problem will be application to the first law using steam tables however. So, let us now come to question number A, or the first problem of this tutorial. Please understand the problem. Steam at 10 bar pressure passes through a pipe and expands to 0.1 bar in a throttling device. So, the state at 1.1 is going to be 10 bar and state after expansion is going to be 0.1 bar, and this process of expansion is by throttling device, meaning which it is an isenthalpic process. Enthalpy remains constant from 1 to 2. The temperature of steam after expansion is 100 degrees centigrade. So, we know the pressure P2 and we know the temperature T2. Find the state of the fluid before expansion. So, I need to know all the things at 0.1 where I only know the pressure. So, temperature T1, dryness fraction if any, enthalpy H1, entropy S1, etc. The hint is one can use Mollier chart for this solution. One can solve this problem even using steam tables, and if you try using steam table you will find it very difficult. The problem become very simple if you use Mollier chart for this. Alright. So, let us solve this problem. Tutorial 4 question A. What is given to us? We have got state 1 and we have got state 2. What we know about state 1 is P1 is equal to 10 bar or 1 MPa, and P2 is equal to 0.1 bar is equal to 0.01 MPa. Also, what has been told is the temperature after expansion which happens from 1 to 2. So, T2 is equal to 100 degree centigrade or 373 Kelvin. We know that the process from 1 to 2 is isenthalpic throttling process, alright, which means that H1 is equal to H2. Alright. So, what we can do is using HS diagram or Mollier chart, we can easily locate the state 2 because we know two properties P2 and T2. So, locate point 2 on this Mollier chart, and being a isenthalpic process from 1 to 2, from 2 we can get state 1. Alright. So, let us go to now the Mollier chart and understand what it shows. Alright. So, from here I will go to the Mollier chart, and this is the Mollier chart. From here I will locate now the state 2, which is P2 is equal to 0.1 bar or 0.01 MPa, and T2 is equal to 100 degree centigrade. So, I can highlight the place where I want to go. Alright. So, here I can go here and locate the point of 0.1 bar, which is from here you can see this blue line, and T is equal to 100 degree centigrade, which is 373 Kelvin. Alright. So, somewhere here my state 1 will be, sorry, this will be my state 2 because this is after expansion. Alright. So, this is my state 2 and therefore I can locate that state 2 over here. Alright, so this is state 2, and I know that the state 1 to state 2 process, 1 to 2 process is isenthalpic process, and the y axis being enthalpy axis, I can just draw a horizontal line passing through this point 2, and on this line somewhere the point 1 would lie. That is what I know. Alright. So what I do, just draw a horizontal line, and I would like to see now, because the state 1, other thing also I know about state 1 is the pressure. The pressure before expansion is 10 bar, that is what has been told given in a problem. So I can go now again closer to this and locate the intersection of this isenthalpic line with pressure equal to 10 bar, which is this. So you can see that as soon as I start locating, I come inside the dome here, and therefore it indicates to me that the state will be now here a 2-phase zone or the wet steam, while the state 2 is superheated zone, which I could see directly. The state 1 happens to be the wet steam, and the point would lie somewhere over here. So just show the point 1 in this steam now, in this diagram. So this is where my state 1 lies, and corresponding to this state 1 now, I can read other values, other properties like x and also the temperature. So can I see the temperature again? Right. So you can see the temperature being somewhere 423 Kelvin, alright, somewhere around this point, and also I can see that the x could be somewhere in between 90 to 100, let us say around 95%, etc. So I can get all the properties for these from this diagram now. If I just want to draw vertical, and so enthalpy is 2700, I get entropy value at state 1, which is around this, could be around 6.5, alright, and corresponding to point 2 also I get this value. So I can again come back to calculation. I understand from this diagram the data which I got for state 1 now from here, which is what the question was, is the temperature T1 is equal to 150 degree centigrade. The x1 from here, if I do proper interpolation, I can see that it is 0.96. Corresponding enthalpy is 2700, which we have seen from the Mollier chart, and entropy also we could see that it is 6.2 kilojoule per kg Kelvin. So this is what my state 1, and that is what was asked in the problem. So if I go to my slides and write down the answers properly, I can get the answers as T1 equal to 150 degree centigrade, x1 is equal to 0.96, h1 is equal to 2700 kilojoule per kg, and S1 is equal to 6.2 kilojoule per kg Kelvin. One can appreciate from this problem how efficiently we could get these answers from the Mollier chart, and that is the purpose. That is, I could understand that the state 1 lies in 2-phase region, while I could understand state 2 lies in a superheated zone, which one could see directly from the Mollier chart. I did not have to do any calculations further to understand these aspects. Thank you very much.